Okay, let me start recording and let me go back to share screen mode. Okay, let me continue. So basically, how does it look like? So here you may see classical system, how based on laser diagnostics, you can trace particles and respectively trace the flow. So what you see here, so here is, let's assume you consider some kind of a tunnel or a pipe and which flow goes. So here is your flow. Flow direction is shown here by these arrows. You see it's flow with pressure particles, that's how it goes. So what happened? Here you have, so what you do, if it was a flow, you would not see anything, right? You would not see how flow goes. It will be just color liquid. Now you have laser, you deposit particles here. So laser is rejected through this mirror, and that's how you eliminate the particles. So what happens here, and then you track the particles. You make many pictures, many photos, and you will see. For instance, what happened, you may realize, so there are different particles. And based on how flow goes, these particles will change trajectory. Does it make sense? So if it, let's assume it was really laminar flow, really laminar, really like shear layer with all parallel streamlines. So what would happen? Let's say I track particles. So if it was plain parallel, picture on like here solid points like field markers show you here initial stage at time t, and open markers show what would happen later is t prime at some other time instance. So if I have classical laminar flow, what would happen? Then they move to the regular, it will be like this. So the distance between these three particles, this group of particles will not change. They will be plain parallel. Does it make sense? I hope. But if you have turbulence, definitely the distribution between particles will be different. As a result, really, they will change. And based on how they change, based on how distance between has changed, you can really treat and describe the flow. That's why remember your midterm exam and remember your first lecture when I told you that turbulence, it's a collective motion. And even now we don't talk about flow, we talk about particles. You may realize that if it was one particle, right, you wouldn't see any turbulent action. It will be just shift. You should have several particles, and it's collective item. And when the collective interaction is changing, then it means that you can quantify your turbulence. Well, what we have here, I will skip some slides here. Definitely, we are limited of time today, but definitely you may see here the different laser light optics here, and you may see you will have different lenses which increase, decrease light, which focus to show how particles go. And basically, what I want to show you that basically you can see if you what happens here that you investigate based on sensors, you investigate fluid particle interaction plus particle interaction with light. Well, what you see here is classical Stokes formula. There is drag law, Stokes drag law. It shows how the velocity, how drag velocity depends on what? On the particle size, on viscosity, and on the difference between particle density and density of the flow. And then similarly, as long as I have acceleration or deceleration, this will be my shift velocity. So what you can see from here, and what is really important, if density of particles is exactly the same as density of the flow, then you will see nothing, right? This value will be 0. What does it mean and why? It's key point that what we call seed, we call this particle, sometimes we call it seed because we put it there. Seed density should be different from fluid density. So you may realize that if the density will be the same, nothing will be happening here. Why? Because remember, fluid mechanics does not know chemistry. Fluid mechanics does not know thermodynamics. Fluid mechanics does not know reactions. From fluid mechanics know what is velocity and what is density. So how fluid mechanics knows the difference between solid particles and liquid particles? Only because they have different densities. Do you understand this? And because they have different densities, they generate extra volumes, they have drag force, and they may generate different flow interaction because it is momentum which is conserved in fluid mechanics. So when you have density variations, when density is changing, it means that you have velocity variations. Okay, so now what kind of particles people may consider? That's good. And basically, when I say particles, it's not necessarily solid particles. So please see what people use, what particles people deposit for velocity, for uh, PIV measurements, particle velocimetry measurements. And if you ask what particles to use, first of all, we should ask the following: what are we measuring? What turbulence we talk about? Do we talk about liquid, or do we talk about gaseous flows? Why it's important? What do you think? Answer is very simple. Uh, if you deal with liquids, remember what is liquid. What is the difference between gas and liquid? Gas is a rarefied flow. In the gas flow, distance between particles is quite big. In the gas flow, we don't have actually viscous effect as we have in liquid flow. In liquid, we do have. So when we deal with liquid flows, viscosity is crucial point. Mean free path length is crucial point. So that's what people use as a classical materials to measure. So sometimes people use solid particles like polystyrene, aluminum flakes, aluminum particles. Sometimes people use simply glass spheres, hollow glass spheres, granulars from coating, something like this. So, and here what you may see what size of the particles in microns, in micrometers. You may see that your particles should be really, really small. It should be like from 10 to, if you talk about solid particles, it should be from 10 to 100 micrometers. Why? Because solid particles, they're really stable, they're not, they're elastic, and their interaction will be shown on the small scales. So basically, this size should be less than Kolmogorov scale. Now, sometime, as I told you, you don't want to destroy your flow, right? So instead, or in addition to solid particles, you can put liquid or gaseous particles, not particles actually, like impurities, I would say, liquid impurities. Like you may use, for instance, let's say you try to measure turbulence in mercury or in somewhere there. So here you have, when you talk about mercury, you should have different oils here. For instance, you can take some kind of kerosene, some kind of oils, vegetable oil or petroleum-like oil, and then the size of these parcels, the size of the actually droplets, it should be large. It's from 50 to 500 microns. So it's quite big. 500 micron, it's a half millimeter, so it's visible one. Well, sometimes people use gaseous impurities, gaseous bubbles, like oxygen bubbles. Sometimes people also use, why people use oxygen or sometimes nitrogen bubbles, or also ozone bubbles. You know what is ozone? It's like O3 instead of O2. Why? Again, because really this matter is similar to what we have in air. It's like air standard approach. But for oxygen bubbles, they can really be quite big, up to millimeter actually, like this. So that's if you talk about liquid flows, when we really care about small scales, when we really care about transient things. Now, if you talk about gaseous flows, here you may see that your material, gas, what is gas? Gas is very light. So here you need to, and in gas, you do want to have big lengths between, big mean free paths, big distance between particles. So here you really don't want to spoil your gaseous flow, because really your mass, and here you use only quite small particles. So basically, if you use solid particles like aluminum, like titanium, these should be very, very small ones, like from 0.1 to 5 microns. So let's say order of magnitude smaller than this one. Again, if you want gaseous flows, you can use the following liquids, where it is helium, it is some kind of different oils, but all these diameters should be quite small. And here, if you have helium soap, it can be large one because it's light. So now let me ask you, so why it's like this? So why for gaseous flows we use so small particles, while for liquid flows you use larger particles? What do you think about this? Who wants a bonus ticket for this? And here is a picture. You may see how different impurities look like in reaction flows and supersonic flows. That's how it look like. So what do you think about this? The answer was very simple. Again, I told you, by your sampling, you don't want to destroy your flow. Let me say like this. Assume you sit in a class. Now we are all separated in our homes, but assume you sit in the office. And somebody bring very hot piece of metal or very hot firing wood stick. What will happen? You will definitely feel that it's hot, right? You will definitely, let's say it's a very hot piece of metal. So if somebody bring it like to your room, you will definitely see that it's hot, correct? Why? Because your air is rarefied and you actually start preheating your room very fast. But assume now I take this hot piece of metal and drop into some kind of water tank. What will happen? Definitely in water tank, it will sink and it will get cold. Why? Because you know heat conduction of water is almost 100 times higher, 80 something times higher than that. So what does it mean? It means that your hot stick would not spoil, would not change temperature of water much, but would change temperature of your room. Similar analogy is here. When you talk about liquid flow, these big particles would not change it much because the water is really dense. The water is quite strong, quite viscous. And you don't need many particles, right? So particles of this side, total mass fraction of particles that you deposit will not change your water flow, liquid flow. But in gaseous flow, you should take much smaller particles because you need many particles, right? You need many particles to consider, such that overall average mass fraction of particles does not destroy the flow. Does it make sense? And what you do next, you collect signal by a camera and measure it. So that's how it happens. And basically what you're doing, I will finish very soon, but just a couple of formulas. I will continue maybe next time or whatever. So let's see, you have 3 particles at the initial instant, and then you have 3 particles subsequently. And here are the initial coordinates, and here's the next coordinate. So what is happening? You measure as follows. You consider intensity of the flow and find so-called transfer function of the light energy. Based on this, you will get correlations between them. I will talk about this later, but that you see this formula, does it resemble something? Exactly, this is correlation function. So it shows how 2 particles correlate. So basically, based on these measurements, you will see velocity correlations between these particles. Okay, I will stop at this point. I will stop at this point. I will